Welcome to this month's Keck Astronomy Lecture here on the beautiful campus. Can you hear me okay? Excellent. Aloha. Welcome to this month's Keck Astronomy Lecture here on the beautiful campus of the Hawaii Preparatory Academy. And as is tradition, before I introduce tonight's speaker, a bit of science news from what I think is the world's most scientifically productive observatory. So headline news has been pouring in about research published by Keck astronomers about almost every facet of the universe over the past month. And our world-leading adaptive optics system have dominated the discoveries, it just happens, from our telescopes over this period. From weather patterns on Uranus to volcanism on Jupiter's moon Io to the galactic center, our adaptive optics is bringing science that we couldn't have even imagined 20 years ago when the skilled technicians and engineers were putting the final touches on the Keck telescopes. But perhaps the most exciting of the recent news came from tonight's speaker's home institution, UCLA. And earlier this month, UCLA astronomers announced something they had been looking for over a decade, and that is they reported the discovery of a star that gets closer to the black hole at the galactic center than any other that's ever been found. This star has the glamorous name. I think from coming to these lectures, you know that we're not very good as a field at naming things. So the star that came the closest before was discovered with Keck and adaptive optics, and it was called S-02. So that star orbited the galactic center in about 16 years. And this new star that was found because we keep making the adaptive optics system better, and we keep being able to see fainter and fainter stars and stars in more crowded environments, this one is called S-102. So pretty glamorous. But this star is truly amazing. I mean, the acceleration on this star, so the way its velocity changes as it gets closer to the black hole, it can accelerate by more than 250,000 miles per hour per year, and it'll reach a peak speed of about 3 million miles per hour as it whips around the black hole. So this star was found by Andrea Ghez and her colleagues, and Andrea leads the UCLA Keck Galactic Center group, and they've been tracing all these stars as they do this waltz around the galactic center. And as I said, they're trying to get the stars that go the absolute closest so they can see the massive effects of a black hole that weighs more than 3 million times the sun. I mean, you can imagine the gravitational pull of such an object. And as you get close to it, you're actually testing Einstein's general relativity. So that's the big prize here, is to find a star that gets close enough that we can precisely trace its orbit with Keck to test Albert Einstein's predictions in this very extreme environment. So our adaptive optics system, as I said, has been getting better and better year by year, allowing us to see fainter and fainter stars and stars that are more and more crowded into this compact environment. And friends of Keck Observatory, foundations, the National Science Foundation, all have supported these improvements to the adaptive optics system that are so vital to this science, so that we can study this unique environment of the black hole at the galactic center with even more power and precision. So now that I've brought you up to date about the most recent discoveries, it's a real honor to introduce Dr. Benjamin Zuckerman tonight. Ben received his undergraduate degrees from MIT in physics, and then he went up the road to Harvard, where he got his PhD in astronomy in 1968. And you think about 1968, I mean, the Keck telescope wasn't even on the drawing boards then. So Ben has used all sorts of telescopes worldwide to do his research. He's had a long and prestigious career, and he's published many landmark papers. His one area of his expertise, as you'll witness tonight, is how planetary systems around stars form and evolved. He's served as editor of 2 books that deal with really exciting topics in astronomy. Let me give you the titles to give you just a hint of what might be to come. Extraterrestrials, where are they? And the origin and evolution of the universe. Ben also has many interests involving our home planet and is active in several nonprofit organizations committed to Earth's long-term environmental health. So tonight's presentation, he may have the opportunity to weave those together, his science and his personal avocation. So please join me in giving a really warm Waimea welcome to Ben Zuckerman for his very special talk, Violent Events in Rocky Planetary Systems, Implications for the Fate of Technological Civilizations, including our own.
Thanks, Taft, and it's a pleasure to be here, as always. I especially want to thank you, Taft, for reading the title of the long title of my presentation tonight. When I last gave a public lecture at Keck, it was about a half a dozen years or so ago, and we were meeting over in Keck headquarters. And at that time, when I was talking about technological civilizations and our search for them out there, I don't think I mentioned Keck during my presentation, but I'm going to have some good things to say about the Keck telescopes this evening. And in the coming 50 minutes or so, we'll be taking a voyage of 10 billion years from 4.5 billion years or so in the past, when our the solar system was first forming, to 5 or 6 billion years into the future. And the world-leading contributions from the Keck Observatory will come near the end of my presentation. So much astronomy-related media focus these days is on extrasolar planets, especially planets that might be in the so-called habitable zone for life as we know it. And basically, the habitable zone is defined loosely as that region on a planetary surface where water could be in liquid form at least some of the time. And in fact, one of NASA's overarching themes is the search for liquid water, both in our solar system and outside of our solar system. If you find a place where there's liquid water, then there's a possibility that life as we know it might exist. So since the lion's share of the media popularity and popularity also among the astronomical community, and the astronomical community is generated by widespread interest in life in the universe, that's going to be one of the guiding themes during my presentation this evening. So for our own solar system, the story began about 4.5 billion years ago. And here's somebody's theory of rocky planet formation. Sort of takes place in about 3 steps. First, the young sun forms, and it's surrounded by a swirling disk of dust and gas. And then after something like 1 million years or so, give or take, some of the dust particles clump together and form what are called planetesimals. And a typical planetesimal, we think, was probably about the size of, say, Mauna Kea Mountain. That might represent the size of a typical planetesimal 1 million years or so after the sun formed. And one can think also of these planetesimals as being associated with comets or asteroids, some of which survive to the present day. That's what we mean by planetesimals. And then, say, another tens of millions of years go by, and the planetesimals collide with one another, and some of them clump together and make what are called planetary embryos. And these planetary embryos are these big creatures you see over here on the right-hand sketch. Okay, so these are basically growing planets, And you can see there may be a half a dozen or 10 or so of them. And we know in the inner part of our solar system now there are only 4 planets. So this sketch, at least if it was applied to our own planetary system, is before everything sort of worked their way out to their final configuration. So here's a slide which might look a little bit complicated. I promise you only have one other slide that looks even slightly complicated, and this one really isn't as complicated as it might look. So what you see on the vertical axis here is the size of the Earth, the growing Earth, and the current radius of the Earth is about 7,000 kilometers, I guess about 4,000 miles. And on the horizontal axis, this is 10 million years, 20 million years, 30 million years. And basically what we think is the Earth formed over a period of about 30 or 40 million years, and it formed by the collision of various of these planetary embryos. One of these collisions, perhaps the most violent and massive one, was responsible, most astronomers think, for the formation of the Earth's moon. And I'll come back to that in just a few minutes. So that's the picture of how the Earth came together in a period of 30 million years. Now, we can't go back and see that process directly, obviously, because we're 4.5 billion years into the future. But what we can do is we can look at sun-like stars that have ages in the right range, say up to 30 to 100 million years, and look for the evidence of collisions of these planetary embryos. Because when these things come together, there's a lot of violence and a lot of dust produced. And in particular, what we found is that around some stars that we study, especially in the infrared, there's evidence of heat radiation coming out from warm dust particles. And by warm, I mean something like the temperature of your body or the temperature in this room, something similar to the temperature of the Earth. And warm dust orbiting around a sun-like star is sort of like the same distance roughly as the Earth is from our sun. And when you put dust in such an orbit, it can't stay there very long. Small dust particles either get blown away from stars or they spiral into stars. So we know that if there's a lot of warm dust in orbit around a young sun-like star, something violent must have happened, relatively recent, to create all of that dust. And here's an artist's conception of one such collision, of a collision between, say, 2 planetary embryos. Now this drawing by Lynette Cook was actually produced in conjunction with the discovery of a lot of warm dust around the Pleiades star, the sun-like Pleiades star HD 23514. And the picture that we have here is that this star is about 100 million years old, the Pleiades cluster, and I'll show you a picture of that in just a second. It's about 100 million years old. And what we have here is potential for a moon-forming event in this system. We think that because there's so much dust orbiting around the star, HD 23514, dust that was produced some maybe 10,000 years or so, we're not sure exactly how long ago, in the past by a collision like this. A lot of debris came out from that collision. Some of the debris went into orbit around one or maybe even both of these objects, and some of that debris could have conceivably condensed and formed a moon around one or even both of these objects. Again, that's how we think our moon. Astronomers generally, that's by far the most favored theory for the formation of Earth's moon. At any rate, some of the debris goes in orbit around these colliding objects, but some goes in orbit around the central star, and that's the material that we can study now with our infrared telescopes in space and on the surface of the Earth. So here's the Pleiades. It's now high in the sky, the so-called Seven Sisters cluster. If you go out, I think here in Hawaii, you can probably see the Pleiades. In Los Angeles, where I live, it's pretty hopeless. But if you've got really good eyesight and you're in a dark site, you can see Seven Sisters, 7 of the brightest stars in the Pleiades. Now that HD 23514 is none of the 7 brightest stars, but I'll show you exactly where it is. It's where this red arrow is pointing at that star there, which is bright enough that it, with a modest, certainly a modest-sized telescope, maybe even good binoculars, you'd be able to see it. So the Seven Sisters are up here, and just a little bit below them is this star. So we think that right now there are rocky planets forming around that star in the Pleiades. So to summarize this sort of points I've just been making. These are is what we call moon-forming events, and a few stars, young stars, are so dusty in the terrestrial planet zone that we think that there have been violent collisions of massive planetary embryos or even full-fledged planets recently. So that's what's going on around some of these young stars now. I just want to mention some similar events that are taking place around our own sun now in our own solar system, but not as violent because they don't involve such massive objects. This is a picture of the zodiacal light, and basically what you're seeing here is the sun is just set. This is a picture taken from an observatory mountain in southern Spain by Paul Melis back in 1997. It's Comet Hale-Bopp over there. That's the Pleiades up there. And what you're seeing here, though, this great cone of light, the sun is just set, and sunlight is coming and hitting dust particles that are orbiting around the sun at more or less the same distance the Earth orbits around the sun, and some of that sunlight's being reflected in our direction. And the zodiacal light can only be seen in a completely dark sky under really good conditions. Here's another example of the zodiacal light. Just out of curiosity, how many people in the audience have seen the zodiacal light in their lifetimes? Okay, I see maybe 10% have raised their hand. That's, when I give this talk and I ask that question, that's pretty standard. So this is a phenomenon that's not commonly seen. I saw it myself for the first time in an observatory in Chile many years ago, back, it was a long time ago anyway, and I'm not sure I've seen it since, but it was very pronounced there. And I just would like to take a 2-minute digression or 3-minute digression to mention two other atmospheric and astronomical phenomena that are well worth witnessing, and I just want to call these to your attention before I get on with my main story. So again, the second item here is the zodiacal light, which is uncommonly witnessed by people. Again, 10% or so was the number of people raised their hand. This evening is, I find, pretty typical. Now, the green flash is another phenomenon which is, I think, more commonly seen, and let me show you the picture of the green flash. So here's the green flash. One can see this phenomena over the ocean when the horizon is really completely clear of junk and clouds and things like that. And it's basically what happens is for about a second, the upper edge of the setting sun. The sun is just set there, and its very upper edge flashes bright green for about a second. How many people have seen the green flash? Okay. So that's more common. Let me see. I think I have common. Okay. So I got that right. So the green flash is not that hard to see. And actually, many years ago, I saw my first one while standing on a mountainside on the west coast of Maui as I was coming down the mountains there. So my first green flash was seen while I was in Hawaii. Okay, but now here's something that not so many people, I think, have seen. It's a moonbow, and a moonbow is not the ring of light you sometimes see close to and encircling the moon. A moonbow, rather, is similar to a rainbow. And if you imagine that this is, rather than the moon, it's the sun, let's say, then if that was the sun and you wanted to see a rainbow, you'd look over your shoulders in the back. Okay, rainbows appear on the opposite side of the sky from the sun. Same thing happens with moonbows. This is something that the moon, the phenomenon of the moon in conjunction with clouds produces on the opposite side of the sky. And some 20 years or so ago, I was observing on Mauna Kea. I think this is before the Keck telescopes were even built. It was a cloudy night. I gave up about an hour or so before the sun came up and started to drive down from the summit in a Jeep. And there was really clouds swirling about. Again, it was a lousy night for doing astronomy, and this strange lights flashing. And I decided, this is really weird. I'm going to get out of my Jeep and see whether anything interesting is happening. I got out of the Jeep, turned off the lights, and the full moon was on one side of the sky, and the other side of the sky was a moonbow. And I didn't even know moonbows existed, and I was fortunate enough to see this one. So when I got back to Los Angeles, I looked in the book called Light and Color in the Outdoors in the index, and sure enough, there was moonbow in there with a couple of pages about moonbows and even a poem by Schiller from William Tell. Yes, truly, a rainbow in the middle of the night. 'Tis the light of the moon by which it shines. 'Tis a strange and wonderful omen that few people have ever seen. Has anyone here seen a moonbow? Oh, more so than, okay, even more so than zodiac light. Well, that's a little surprising. Yeah, I guess that's true. Okay, right, this is a biased audience. Good point, thank you. Because, yeah, okay. Because I've asked that question elsewhere, and virtually nobody raises their hand. Yes, I would imagine Waimea is a great place to see moonbows. Okay, getting back to the main story then. So nearly 30 years ago, NASA's Infrared Astronomical Satellite discovered a young sun-like star with a prominent ring of warm dust particles around it. And the ring was a radius about half the distance between the Earth and the Sun, about the distance that Mercury orbits around our Sun. And the ring contained about 1 million times more dust than is seen in the Sun's zodiacal cloud, which I just showed you a couple of pictures of. Okay, so this was really a very dusty star. And a few years ago, as part of my former student's thesis, Carl Melis' thesis, he began studying this dust ring as part of his PhD thesis research. He's basically, we're trying to understand how and when rocky planets form around sun-like stars. And what we found, to our amazement, was something not seen in the history of this field, which has been going on for about 30 years now, a disappearing dusty disk. Totally unexpected. And because it was so totally unexpected, when we submitted a paper describing our results to the journal Nature, we had a real adventure. There's an editor who evaluates the paper, and then 3 referees. And they thought we were just screwing up, because how could this massive dusty disk disappear in just a year and a half? And it took us months of fighting with them. They were on the verge of rejecting our paper. We finally convinced them we knew what we were doing, and this was really happening. So this is the second of these relatively complicated graphs, and then there are no more. So let me just describe this to you. This is the spectrum of the star, this really dusty star. If it was plotting the spectrum of our Sun, it would look similar, except it would peak. The peak would be a little bit further towards the left, because this is wavelength down here. So the blue is over on the left and the red is over on the right, except these are infrared wavelengths. So this is the spectrum of the underlying star. And then what the satellites, starting with IRAS, discovered with these points up there, this huge amount of infrared radiation, 10% of the energy of this star was coming out, absorbed by the dust and irradiated at wavelengths similar to the wavelengths you and I radiate at. So this went on for like 25 years, bunch of different ground and space-based telescopes. And then lo and behold, in the space of just a year and a half, this big emission bump disappeared, and this was the result. So this, if you go out and measure the star now, it's going to look like that, and this is all going to be gone, all those points up there. So here's sort of basically what looks like it happened in just a year and a half, that all that dust just disappeared around this star. By the way, the bottom line is nobody, and at this point, has really a very compelling explanation for what went on. What went on with this star in the last couple of years. It's like if you went out and took a picture of Saturn now, and you came back a year and a half later and the rings were gone. So it's like basically this in just a year and a half. But the thing about the rings that were around this star is their diameter was 100 times as big as the diameter of the rings you're seeing around Saturn. So just an amazing disappearance. And again, as I say, nobody really understands at this point what caused that disappearance. Okay, so now I'm going to move forward in time, and we basically have this sort of order 100 million years of many violent collisions, and then we think our solar system emerged with some rocky planets, 4 rocky planets relatively close to the Sun, 4 gas giants further out, and many tens of trillions of leftover planetesimals, mostly in the outer reaches of the system. So like comets, for example, would be what we mean by a planetesimal. So what happened next? Well, the giant planets can interact gravitationally with each other, and the giant planets can move around a bit, and they can interact gravitationally with a substantial planetesimal belt. And there's a favored theory right now among astronomers that something like 600 million years after the Sun formed, the outermost planets, Uranus and Neptune, moved a lot, and the gravity really stirred up the outer planetesimal belt, causing many of these planetesimals to come into the inner solar system, basically deflecting the orbits and causing an era of heavy bombardment. And this is sort of a picture of what many astronomers think went on about 600 million years after the formation of the sun. So you have these are the 4 giant planets, and by certain ways they're interacting with one another gravitationally. Jupiter and Saturn moved a little bit closer to the sun, and Uranus and Neptune moved a little bit further away. And when Neptune advanced into this planetesimal belt, which had tens of trillions of comets and things like that, and back in these early days, it gravitationally deflected some of them into the inner solar system, and those impinged on the Earth-Moon system, among other places, and caused a lot of cratering events and whatnot, this so-called era of heavy bombardment. So that ended about 600 million years after the formation of the sun, and things seemed to stabilize then among the orbits of the planets. And at that, many paleontologists believe that was about the time that life finally was able to take a firm foothold on Earth and basically get started and evolve to what we have today. But no one really has a clue as to how life started on Earth. So that was 600 million years after the formation of the sun. Then there are billions of years more before we emerge on the scene. So during these billions of years, there must have been occasionally some pretty violent activity, massive volcanism and impact of large bolides, objects, would be asteroids or comets. And the most famous example of such events occurred about 65 million years ago, when a bolide, or some kind of projectile from outer space, hit the Earth in the Gulf of Mexico, near Mexico's Yucatan Peninsula. And this bolide was probably about the size of Mauna Loa Mountain. I would say that's roughly how big it was. It caused a big splash, and according to the way the theory goes, the demise of the final dinosaurs on Earth. So again, this is about 65 million years ago. The last dinosaurs went extinct, supposedly as some kind of, because of this collision of the Earth with this bolide. So that's 65 million years ago, and then 60 million years or so after the dinosaurs disappeared, humanoid creatures, things that maybe looked a little bit like us, began to appear on Earth. And in the few million years since humanoid creatures first began to appear, we've advanced, if that's the right word, so there are now an incredible number of us on Earth. Just how many people are there on Earth? And you hear my numbers like 7 or 8 billion, but I want to put the answer to this question in terms of the vertebrate biomass. Paul McCready, who was the designer of the first solar-powered aircraft, estimated the total weight. He estimated the total weight of all terrestrial and avian vertebrates. And when agriculture began, say, tens of thousands of years ago, our pets and our livestock accounted only for 1/10% of all the vertebrate biomass. But today, we and our domesticated animals account for 98% of the total, and we're using up a lot of Earth's resources in order to support ourselves and our animals. And this is a UN plot of world population growth with projections to the year 2100. So here, the projections one here's about get up in the range of 10 billion plus or minus a billion or so people. We're right now about over here between 7 and 8 billion. And you notice that they sort of, the people who put this plot together sort of decided to throw up their hands, and we don't know what's going to happen after the year 2100, so they just drew a straight line. My personal belief is it's much more likely there's going to be a huge population crash sometime either before or after the year 2100, but I'm not going to be around to witness it. There may be some young people in this room who might be, but I'm not going to be here to witness that crash. And one reason I'm not going to predict for sure whether the population is going to crash is because of my friend, my hero, Yogi Berra, who was a star baseball player for the New York Yankees in the 1950s when I was a boy in New York City. And Yogi has a lot of wonderful quotes like this. He's still alive. And anyway, so now, I mean, we can laugh at a few of these things, but it's really a tragedy because so many voiceless species are being harmed or even exterminated by our explosive growth in population and consumption. And I think there's no doubt that when we're done, we'll be responsible for the worst mass extinction event or extermination event of species on Earth in the past 65 million years. And we very well might be the cause of the absolute worst species extermination event in Earth's entire history by the time we're done. And there's another talk I give. Taft mentioned I have some environmental interests, which doesn't have any astronomy, and it's basically as a title, Population Consumption Overshoot, Can Catastrophes Be Avoided? And I can tell you, or maybe I can hint at what the answer to this question is, but it's not a pleasant one. At any rate, there are a lot of smart people who think we're really in deep doo-doo right now. Most economists don't really have a clue about the environment and sustainability, but there are a few exceptions. Herman Daly's a great economist, and it's a wonderful quote from, "We're treating the planet as if it were business in liquidation." And here we are in the middle of the biggest body of water we know of in the universe. Remember, NASA's out there looking for water somewhere else, while we on Earth here are destroying life in the big oceans. And Jacques Cousteau, and many of you obviously are old enough to remember him. He died about 15 years ago, but he was a famed explorer of the oceans. And this was before we had climate change and before we had the temperature of the oceans rising or acidification of the oceans because of all the carbon dioxide that's going from fossil fuels into the oceans. Way back in the 1990s, he was already saying, just due to pollution and overfishing and damming of rivers and everything, that the oceans are dying. So we're killing life in the oceans here while we're looking for water to support life out there. It's a little ironical. A big question I ask in my other talks, I'm not going to try and, I ask and I try and answer it a little bit. I'm not going to spend much time in this talk today, but are we capable of devising any sustainable economic and political system, especially one that's able to deal with 10 billion of us? Right now, capitalism pretty much has the run of the world. And in my personal opinion, there is no way that capitalism, certainly not the way it's practiced now, can possibly be sustainable. But that doesn't mean that other systems humans have devised, like Soviet communism or 20th century Nazism or fascism, are any better. The real question, this is the big question, can we find a sustainable system of any sort that can deal with anything like the populations that now exist on the Earth? And here's a question I asked this, and before, I'm almost ready to leave the present time, but I want to relate one short story from 100 years ago before we move on to the future. So that story relates to my question, are humans any smarter than deer? And this is a story about our so-called great environmental president, Teddy Roosevelt, who was president about 100 years ago, and it's a story of the deer in the North Kaibab National Forest, which is just the north of the Grand Canyon. Back 100 years ago, Teddy Roosevelt decided that the mountain lions that lived in this forest were vermin, so he ordered them all to be exterminated. So the mountain lions were killed off. The deer population exploded because there were no predators anymore, and the deer population exploded. They overbrowsed their resource, and then after this great explosion of deer population, the population crashed dramatically. So when all was said and done and things settled out, there were fewer deer in the North Kaibab National Forest than when the mountain lions were living there and predating on the deer. Now, human beings have no predators other than ourselves, and I just wonder, given that UN curve, whether we're any smarter than the deer. And one person that Taft mentioned in his introduction, who's a pretty smart fellow, I think doesn't think we're any smarter than deer. This is my favorite Albert Einstein quote. Only two things are infinite, human stupidity and the universe, and I'm not sure about the latter. Okay, so just sort of summarizing the current situation, we're responsible, what we're doing now, this is really a violent event that's taking place in our biosphere. It's one of the most violent events in the history of of the biosphere, and an impoverished biosphere is a certain outcome from what we're doing now. But let's move on into the future now. We've all heard about human-induced global warming, but the warming I'm going to focus on now in the future is that due to the slow but steady increase in the luminosity of our sun over billions of years. And about 1 billion years from now, the sun should be luminous enough that the oceans are going to boil away if something isn't done. Now that sounds like a pretty disastrous kind of a thing, right? Devastating fate, oceans boiling away. Well, I'm aware of 2 suggested possible remedies to prevent the oceans boiling away. The first one, which seems to be the simpler of these 2 suggestions, is just to put a big shield between the sun and the earth and partially block the flux of sunlight that hits the earth. So even the sun's getting more luminous, we don't let all the sunlight hit the earth. The second is an interesting and somewhat more complicated way to dealing with the increasing luminosity of the sun, and that is, by the time 1 billion years passes, we should have some pretty powerful technology. What we do is we go out to the asteroid belt and we grab a renewable slingshot, which is a big asteroid, and we transfer angular momentum between the Earth and Venus. So Earth moves slowly outward and Venus moves slowly inward. And in our space program, we use techniques like this a lot. When NASA sends probes to the outer solar system, we don't have enough energy really to get all the way out there, so we send the probe, say, near the planet Jupiter, and the probe picks up some energy from Jupiter and is accelerated and able to get out to the outer solar system. So that's similar to this idea here, and let me describe it to you. Just have a spot of water. So this is a sketch of the inner solar system, and I think everything's pretty clear. These dots out there represent the asteroid belt. So this picture, the picture of what we might do 1 billion years from now or something, is grab one of these, change the orbits of one of these big asteroids, and have it come in and basically sort of do loop-de-loops, so figure eights around the orbits of Venus and the Earth, and use it to transfer orbital angular momentum such that Venus moves in closer to the sun and gets even hotter, but the Earth moves slowly away from the sun. And so even though the sun's getting more luminous, by moving the Earth further away, the Earth's temperature can stay more or less what it is at present. The oceans won't boil away. But there's a possibility if we mess around with planetary orbits, perhaps we'll cause some undesirable outcomes. And one possibility that we might consider is destabilization of planetary orbits so that there's a planetary collision among some of the rocky planets in the inner part of our solar system. This leads to a question that actually some of the brightest scientists of the last 100 years have addressed. Is our solar system stable? And the French scientists especially seem to enjoy worrying about this question. Lagrange, Laplace, Poincaré, some great scientists a few hundred years ago. And recently a French astronomer, Jacques Lescar, has devoted much of his career to trying to answer this question, whether the solar system is stable. Let me just show you some of his recent results. So this, I have a little movie to show you, but just to set the stage here so you know what you're seeing in the movie. These 4 colored rings are the rocky planets in our solar system. So there's Mercury, Venus, Earth, and Mars. This is what they've done. They've done computer calculations running millions of orbits of the planets into the future. And this is just 1,000 years from now or something. Nothing really has happened. But if you go 3.5 billion years into the future, then in some fraction of the cases, they keep running these programs in slightly different initial conditions. The system's what's called chaotic, and you can get very different outcomes in some cases. So maybe in 1 in 100 or 1 in 1,000 times, they find that some of the planetary orbits actually will cross one another after billions of years. Now again, this is not probable, but it's possible. And so here's with Mercury's orbit is crossing that of Venus. This one down here in the lower left is, let's see, it looks like Earth and Mars, and then the one in the lower right is the Earth and Venus. So let me So I'm not going to say anything because hopefully the words are pretty self-explanatory. So G is billions of years. Giga years is billions of years. So again, this is happening in maybe 1% or 1/10% of the number of cases they run in their massive computer programs. So there was Mars hitting the Earth. That looks unpleasant. Worlds collide, yeah, right, but it wasn't Mars in that movie. It was from some other planetary system. There's Venus. Yuck. So these calculations were done in conjunction with a paper that appeared in the journal Nature in 2009. Well, actually, remarkably, we know of one system which two rocky planets have almost certainly or very likely collided recently. This is star BD plus 2307, which is located about 300 light years from the Earth, and which is actually two sun-like stars that orbit each other in only about three and a half days. And here's an artist's conception of what happened not all that long ago at BD plus 2307. So here are the two sun-like stars. They orbit around one another in only about 3.5 days. Here's a planet which looks like it's got water and continents and whatnot on it, because this system we think is at least 1 billion years old and might even be as old as the sun, colliding with another planet and spewing out all this stuff. And the reason we know that something dramatic has happened to this star is we measure in the infrared a huge amount of emission from dust particles around this binary sun system. And again, this system has like 1 million times more dust orbiting around these stars than the sun has orbiting around itself in the zodiacal light. Okay, well, let's optimistically assume that the Earth escapes all these various destructive possibilities during the next 4 to 5 billion years, while the sun is sort of an ordinary main sequence star. But at that point, at some point, the sun will really get serious and really start to expand in a major way and become a giant star. And while the sun is a giant star, it's going to gobble up Mercury and Venus and possibly the Earth. A lot of people have done calculations as to whether the Earth is going to get gobbled up or not, and it's still, I think the jury is still out on that. In any event, while the sun is expanding, it's losing mass being via strong outflowing wind. The sun is losing mass now in a wind, but this wind is far, far stronger in these future times than it is now. In fact, the sun's going to lose about half its mass during this period, and because the sun's mass will become smaller, the planets that don't get gobbled up by the expanding sun, such as from Mars and on out, their orbits will actually expand, and they'll end up about twice as far from the sun as they are now. So 5 billion years or so from now, what we anticipate is an extended planetary system, but one containing only the planets from Mars on out. The interplanetary part of the system should be quite devoid of material. I'll come back to that in just a second. In addition, the sun will be a white dwarf star, become a white dwarf star with a mass about half its current mass and a radius about equal to that of the Earth. And here's a little diagram of sort of a typical white dwarf star. So there's the white dwarf with about the size of the Earth, but half the mass of the sun. So you cram a huge amount of material into the white dwarf, and its gravity is about 100,000 times stronger than the gravity of here on Earth. Now, remarkably, astronomers during the past few years have discovered that ancient planetary systems exist around probably at least as many as 30% of all white dwarfs. And the Keck telescopes have been the unquestioned world leader in this particular field of research. So here's the inner solar system now, and again, after the sun spends its time as a red giant star, all this stuff should be cleared out, and everything should be sitting out here where the asteroid belt is, or even further out. So that's what we expect, but what we have found astronomers have found, is that there are systems with lots of dust orbiting around these white dwarf stars. So there's the white dwarf, and now rather than this region really close to it being totally devoid of material, there's this ring of dust and gas, which is a diameter now of about the diameter of our sun. So remember, the white dwarf is the size of the Earth, and the ring around it of dust and gas has a diameter about the size of the sun. Well, how in the world did that happen? And nobody knows for sure, but I'll give you two possible mechanisms how, after this cleansing process, when the sun was a red giant, now there can still be stuff when the sun will become a red giant, and these white dwarfs were previously red giants. So how do they have stuff so close around them after having gone through this red giant phase? Well, one possibility, a likely one, I would say, is there are major planets, maybe like Jupiter or whatnot, out in the survive the red giant phase that preceded the white dwarf phase, and the gravity of these major planets deflects the orbits of small objects like asteroids in towards the white dwarf, and so changes the orbit completely, and these things go in towards the white dwarf, and they get too close to the white dwarf. Even if they don't hit the white dwarf, they get torn apart by what are called tidal forces, and Saturn's rings are a good example of that. Saturn's rings are so close to Saturn that big objects held together by gravity can't survive, and so the material gets torn apart. And that's basically what's happened in these white dwarfs. These asteroids get tossed into the tidal radius of the white dwarf and torn apart. And that's one way to get stuff in. Another way to get stuff in is to have a collision of two of the major planets. So here I'm going back to the system I showed you, but pretend there's a white dwarf at the center there. When you have all this stuff coming out in all directions, some of it's coming out in the direction it's going to take it in towards the center of the system. So this is a second way to get stuff in close to these white dwarfs. It can have violent collisions, and some of the material just gets ejected in towards the white dwarf, even though the region was initially cleared out. Okay, so I want to tell you so next, the last thing I want to chat with you about this evening is how the Keck Observatory has played a major role in the work and studying material around these white dwarfs. So here's a picture of the two Keck telescopes with the domes closed, and here's one with the domes open. And this is a table which gives a listing of all the white dwarfs known with 8 or more elements detected in their atmospheres optically on the Keck telescope. This is essentially all data obtained with the high-res spectrometer and the Keck telescope. And basically what happens is the material, just go back here, material in this dust ring eventually finds its way onto the white dwarf, onto the atmosphere of the white dwarf. And once it does that, we can measure the elements that are there and their relative abundances. So here's GD 362, which is the most heavily polluted of these white dwarfs, and there are, I think, about 16 or so elements that have been seen in the atmosphere of this white dwarf star. And we think they're basically, it's accreted asteroids, or maybe even an object as big as the planet Mars. Something like the planet Mars could have been ejected into the tidal zone of this white dwarf and eventually accreted onto the white dwarf. And so we can measure the elemental composition of the rocky bodies that once orbited this star, and all these stars for that matter. And there's some elements here that are very familiar to us all: sodium, magnesium, aluminum, iron. But there's some rare elements too. Scandium and strontium, for example, are two elements. And here are some Keck spectra of with high-res. These are basically where we get signatures of scandium on the right and strontium on the left. I didn't even know scandium was an was an element until we discovered it in this white dwarf. And in our sun, both these elements are down by a factor of 1 billion or so from the abundance of hydrogen, which is the sun's main element. So when you put these kinds of pictures, measure the ratio of the abundances of all these various elements, you can begin to say something about what kind of solid rocky planets orbit around other stars. This is the first time we've ever really been able to do this in the history of astronomy. And the 0th order thing we're finding so far is that most of these rocky planets seem to have elemental compositions that are quite similar to the composition of our Earth, although there's definitely some differences, but that's sort of the 0th order picture. But in principle, we could discover ice-rich planets, iron-rich planets, planets made largely out of carbon rather than silicon and oxygen and whatnot. So that's the kind of science that can come, and it's already coming from observations with the high-res spectrometer on the Keck telescope. And just to summarize what we've learned from these observations is that at least 30% or so of these ancient stars have rocky objects and probably major planets orbiting around them, and that these rocky objects, the total mass of the rocky objects is quite substantial. It's comparable to or even greater than the mass of the asteroid belt that orbits around our sun. And again, this discovery that's sort of described or summarized in this slide is a result of measurements made on the Keck telescope. So let me just conclude now with a couple of slides that have to do with technological life in the galaxy. This is the title or the first page of an article that I wrote that was published in the Quarterly Journal of the Royal Astronomical Society back in 1985, so I guess 27 years ago. And so the title, Stellar Evolution, Motivation for Mass Interstellar Migrations, and I'm just going to read the first sentence of the summary to you. The ease and likelihood, so I'm basically reading these words here, the ease and likelihood of interstellar rocket travel is a much debated issue which is relevant to another controversial topic, the value of capital N, the number of technological civilizations in our Milky Way galaxy. And if one looks at the literature on technological life in our galaxy, one finds estimates for the number of technological civilizations ranging all the way from 1, us, up to numbers of 100,000 or larger. And if any of you were at my talk 6 years ago, you know that I'm one of the people who were in this group here. But anyway, doesn't matter. The point of tonight's, the few words I'll be saying in just the coming minutes, is that this stellar evolution that I've just gone through can tell us something, I think, about the value of capital N. And let me describe that briefly. This is basically what the arguments or the discussion I went through in this paper. The calculations I did suggested that something like a few percent of all technological civilizations in the Milky Way in our galaxy will have been forced to choose between one of two possibilities. Either stay in orbit around their home star while it becomes a red giant, and you got to move really far out if you don't want to have things boiling away and having yourself fried. And then after the red giant phase, the luminous phase is over, and the star becomes a white dwarf when it has a much lower luminosity than our sun. Then you got to move in close to it if you want to capture some of that energy coming out of the white dwarf. So that's one possibility. You just, everybody, whatever creatures are around, billion-year-old creatures or something like that, whatever that they may look like, first they move out and then they move in. That's one possibility. The other possibility is that these creatures may undertake a mass migration to other more stable stars, main sequence stars, stars like our sun, which can be stable for billions of years. Some of the lowest mass stars in our galaxy, the M-type stars, can be stable for trillions of years. That might be really a nice place to go. At any rate, these are the two possibilities. You either take a mass migration or you stay and you deal with the problems of your own star. And given that some civilizations could have had, if there are a lot of civilizations in our galaxy, say if N is a number like 10,000 or 100,000, then some of them must have had a long head start on us and have already had to deal with this fate of the change, the dramatic evolution of their star. And some of those civilizations may have chosen to migrate. And once you've got lots of creatures, in our case we got 10 billion of us, or we'll soon have 10 billion, and once you get out into interplanetary space you get even more. Anyway, we've got lots and lots of creatures. A lot of them may decide they want to migrate for whatever reason. You can think of lots of reasons. And so if there are lots of technological civilizations and they've sent gazillions of creatures out into the galaxy, where this is the cover of the first edition of the book I edited, where are they? And I think this is a real problem for people who think there are tens of thousands or hundreds of thousands of technological civilizations, because again, a lot of them would have to deal with these factors of stellar evolution I've gone through this evening. So I frankly think that this is one of various arguments as to why technological civilizations must be very, very uncommon, very rare in our galaxy. So let me just, rather than leave this question here, let me just, the last slide then is a painting that John Lomberg, who's in the audience tonight, I believe, an artist who lives here on the Big Island, showing the Earth. And I think this is sort of perfectly describes some of the points I was trying to make in my discussion tonight. So thanks for listening.